All right, let's go ahead and take a peek into the wireless side of things. Now, there are some standard comparisons here we're going to take a peek at here real quickly. And basically what it comes down to is the different 802.11 protocols that are used, such as A, B, G, N, and AC, which have been released in various dates and have also different frequency rates, different throughput, data throughput, and so forth as well, right? Radius in and out, and so forth as they differ. And of course, different modulation techniques. And here, just really very quickly, we have what's called the frequency hopping spread spectrum. It's a method of transmitting your radio signals by rapidly switching a carrier among many frequency channels using a pseudo-random sequence known both to the transmitter and the receiver. We have what's called the OFDM, your orthogonal frequency division multiplexing. And this is also a method of encoding digital data onto multiple carrier frequencies. And then we have the DSSS, your direct sequence spread spectrum. It is a transmission technology used in transmissions where data signal at the sending station is combined with a higher rate bit sequence or chipping code that divides the user data according to its spreading ratio. Again, that's all good FYI information. Just know we have obviously the different ones out there, but for exam purposes, you're not going to be asked anything on this. Just wanted to kind of set so we all know what we're talking about when it comes to the wireless side. All right, then you're probably familiar with hopefully some of this information. And when you're going out there purchasing a new wireless access point, for instance, of course, you're going to be probably using something like GN or even AC at the higher rates and so forth. Okay, now with that in mind, we have what's called the SSID, or the service set identity. And basically it's the wireless network name. Right? The SSID is the service set identifier or network name for the basic server set, as in the BSS. It's up to a 32 characters, case-sensitive name used to identify the wireless network. We also have what's called the ESSID, and it's the same as the SSID, but it's used across multiple access points as part of the same wireless LAN. The BSSID is the MAC address of the access points of that service set. Now what we could do is we could disable that SSID broadcast. However, it will not provide efficient security on its own. It can still be sniffed from a wireless network, as the clients have to transmit to associate with the network. We can also force a client to send and announce the SSID by transmitting specially crafted packets, which we'll talk about here shortly. Other things we can do, of course, to help protect ourselves is to actually do MAC filtering. And remember, the MAC address kind of goes into what we call the physical address of the network card. So we're definitely going to need the MAC address information when it comes to cracking WEP and cracking WPA. We're going to need that SSID also, most likely, and so forth. Right? So we'll talk about a few of those items there as well. MAC addresses are easily sniffed by the attacker since they must be communicated in clear text, even with WEP and WPA, in order for the receiver to obtain the transmission. Now, an attacker can also masquerade as a valid MAC address by MAC spoofing the wireless card, which is something we commonly do out there. And of course, if you have MAC filtering going on, we can figure out what that MAC is, and then we can spoof our MAC to be the same as yours. Kick you off the network by doing a disassociate or deauthentication, and voila, we then get on as the target or as one of the clients that is allowable on that network, and we prevent them from getting onto the network because we already have that MAC address on, and we can't have the same MAC address on the same network, so thus you effectively have caused in a sense, denial of service against the user because they now cannot connect anymore to that access point. And here we get into some of the different ways we protect our access points. Obviously, we have the wired equivalent privacy, also known as WEP, security system that uses a static key for both sides of the wireless transmission to encrypt data for secure transmission. The WEP encryption method is designed to provide the equivalent security available in wired networks, and it provides authentication and encryption here. It uses RC4 for confidentiality. It has 64 and 128-bit RC4 keys, uses non-standard extensions such as 256 and 512-bit keys. And the keys are constructed of a 24-bit what we call initialization vector. And the remaining 40, 104 bits are going to be the user-defined key. Now the IV is a rolling counter used to change the entire key packet. It uses what's called the cyclic redundancy check 32 for integrity. And to see what it looks like here, in this screen here, we get to see that we have the 24-bit IV and the 104-bit key on the 128-bit. And on the 64-bit, obviously we have 24 bits and then 40. Now you can see some of the issues there, right? So when we have a busy access point sending around 1,500 bytes packets at 11 megabits per second, after about 5 hours, we'll actually exhaust all of the IVs possible within that 24-bit. So a 24-bit IV has a 50% probability that it will repeat after 5,000 packets. And modern attacks generally here can crack captured or live wireless web encrypted data in less than 3 minutes. And we can pretty much say it's in less than a minute nowadays. Hopefully you're not using WEP, and hopefully WEP is not used within the organization that you're with, because it is definitely one that is not very secure anymore at all. Now, what happens is, so here again, some of the weaknesses that the IVs are transmitted in clear text in the header of the packet, which reduces the length of the overall key by 24 bits. Right? Some of the IV strings reveal certain bytes of the remaining user key. These IV strings are also known as weak IVs. The web key is universal for all web clients. This allows more traffic to be transmitted with the same key. However, here too, the WEP does not check for retransmissions of the same packet. So this means that the attacker can use a replay certain packets here onto the network without it causing any alarms to go off and so forth. And not only that, but we can also send it at 1,000 times the rate than what it would normally go at. And again, not causing any alerts necessarily to go off on that and so forth. Pretty nifty stuff. And we'll be talking about some of those tools here later, like the AirCrack and G suite of tools and some of the tools we can use within that to do those types of things. Then we have what's called the XOR operation, which hopefully you've heard of before or not. But basically when it comes down to what you need to know about XORing is how it compares the two and what the output is there. So when discussing web encryption, it's important to understand the exclusive OR gate, or the XOR, because it's used in the encryption process. And basically, very simple, it's simple comparison of binary bits, and the output is the result of the difference between the two bits. If the compared bits match, the output is 0. If they don't match, the output is 1. And keep it as simple as that, and you'll be able to be fine on any kind of XOR questions that you maybe get. Just again, if the compared bits match, the output is 0. If they do not match, the output is 1. Keep it simple and you'll be fine. Now when it comes to WPA, it improves on WEP because the IV length actually goes from 24 bits to 48 bits. That is very important to remember. Therefore, the reuse of the IV value is less likely. IVs are now used as a sequence counter in the TSC, as in your TKIP sequence number. This prevents encrypted traffic from being replayed onto the network. Now, weak IV values have been eradicated since WPA avoids using known weak IV values. And how it improves? Well, it does this through master keys. Since static master keys are never used directly in WPA, or in WEP they are, in WPA the hierarchy of keys is used, and each client uses a different encryption key thereof. The key management, secure key management here isn't an issue with WPA due to the key generation system. And we have what's called MICHAEL, or the message integrity checking. So WPA uses the message integrity check known as MICHAEL. Although relatively simple, there's 1 in a million chance of guessing the MICHAEL value. This prevents attackers from actually altering packets of the data. And then we have what's called the temporal key integrity protocol. And it was basically designed to allow WEP to be upgraded. It's basically a wraparound web encryption, but addresses the weaknesses associated with the key generation process. The keys are generated dynamically on a per client basis, which means that each and every client uses a different key. Now, the keys generated from a hashing function called the HMAC MD5, based on your MAC of the access point, right, the MAC address, the BSSID, the nonce from an AP, which is just a random number from the access point that it uses. It uses the MAC address of the client, the nonce of the client, the SSID, obviously, and then the pre-shared key or radius key generation. And the nice thing here, when it does all this, it does it in clear text, which is pretty cool. So if the attacker sends 2 packets of unauthorized data during a 1-second period, The system here will assume that it's under attack and shut itself down. The shutdown is meant to prevent attacks, but could trigger ongoing series of shutdowns, which could also be called a denial service type scenario. Right? XP Professional, as well as some of your other operating systems, will also automatically attempt to reconnect to a preferred wireless network after it's been disassociated. So if we go in there, we disassociate the client, we can capture that data, because as you can see here, we transmissions the authentication data, right? The access point MAC, the client MAC, the access point nonce, the client nonce, and the SSID, which again is in clear text, which will allow us to grab that data right off the air. We have what's called the 802.11i. This WPA and WPA2 are virtually identical, both derived from the 802.11i, which WPA being an early snapshot of 802.11i. The major differences is the encryption algorithm used. We have RC4 TKIP and AES CCMP respectively, which is your advanced encryption standard counter mode with cipher block chaining message authentication code protocol. You don't have to remember that at all, but keep in mind when it comes down to us grabbing some data and so forth, we need to obviously have a good idea on what's used. So here, just know that it's using, when it comes to WPA2, that it uses 128-bit and CCMP is basically what we're saying, because it uses AES, CCMP, and AES runs at 128 bits. When it comes to the WPA PSK encryption, here sometimes we refer to as the pre-shared key here. However, you may come across something possibly where you also see PSK, but it's more in the Bluetooth arena and so forth. So when we talk about a technique within Bluetooth, right, uses a digital modulation technique to exchange information between paired devices. This is also known as PSK, but not with a pre-shared key like it is in the wireless world here. But here, PSK would be the phase shift keying that would be used, again, specifically for Bluetooth devices, and that may be important to remember there. Okay, needless to say, remember here that the key generation from the MAC access point, the nonce of the access point, the MAC of the client, the nonce of the client, the PSK, your pre-shared key in this case, and the SSID. All the information as discussed in the previous slide has been transmitted in clear text except for the PSK, right, the pre-shared key, when the client associates. So if the attacker is able to intercept the traffic, they can take a PSK from a dictionary file, combine it with the rest of the data. The attacker can then compare the MICO value until a match is found. Most administrators generally use weak dictionary-based passwords, as in base keys, that they believe WPA encryption is much more secure than WEP, but it's only true if the PSK is long and complex. And generally here we're saying 20 plus characters and so forth. Now if you look at your PSK in implementation using WPA2, most likely it's less than 20 characters, right, when it comes down to that. Now for us to actually grab the information for WPA2 and such, is we must capture what we call the WPA2 authentication handshake. And this is where we basically get some information regarding that information that's being brought out there, like the MAC of the access point, the nonce, the MAC of the client, and so forth, right? And once we have that, it basically generates what we call the WPA authentication handshake. Once we have that handshake, then we can pop up our AirCrack NG suite and run it from there and actually gain access then to hopefully the pre-shared key information and so forth. Remember that the IV key size in WPA2 is 48, right? It's not 24 like it is with WEP, but it is 48 as well. We also have LEAP, which is your lightweight extensible authentication protocol. And LEAP actually goes down to its proprietary wireless LAN authentication method developed by Cisco. And what happens there is it has what's called dynamic WEP keys. And LEAP allows for clients to re-authenticate frequently. So upon each successful authentication, the client acquires a new WEP key. Here it's hoping that the WEP key don't live long enough to be cracked. It does provide mutual authentication between the client, as in the wireless client, and a radius server. And your radius server is basically used in the domain environment. It's your remote authentication dial-in user service server. And it works also in conjunction a lot of times with your domain controller and your domain controller then with your certificate authorities and so forth, provided all within what we call the PKI, your public key infrastructure. Okay, anyhow. The LEAP also uses modified versions of MS-CHAP, which here the authentication protocol in which user credentials are not strongly protected in particular. Now, to find out some of these things, we can do what's called ward driving. And ward driving is something that you'll need to know, is because it's basically a way to go out there and find wireless access points as we go out there and we drive around using a tool like NetStumbler. And again, NetStumbler is going to be used specifically for you collecting wireless packet data. There's also other tools out there that we can use for that. We'll mention another one here next. We also have, when it comes down to the wireless communication and using things like NetStumbler, antennas are going to be also important, which basically comes down to using omnidirectional antennas, which are generally going to be used for wireless communication. So it basically goes around, and it's not like your unidirectional where it's straight one shot from A to B, but it's more like surrounding and so forth when it comes to wireless. So it's called omnidirectional is what's going to be used for your wireless side of things there. Okay. Now other things here, what's really nice is that it will also go out there and identify your wireless access points that are not broadcasting your SSID, which is pretty cool. So if the transmission of the SSID has been disabled, NetStumbler can still detect the WLAN, but it will not display the SSID until the client associates. Pretty cool stuff. We also have Kismet. This is 802.11 wireless network discovery tool and logger. Here, any wireless card which is capable of reporting raw packets should also work with Kismet. You can check out the aircrack-ng .org website, and you'll find that it'll have a listing of all of the different network cards that will work with Kismet and such, because it all has to do with firmware that's running on the card. It's excellent for analyzing a target network, and it will attempt to basically put the wireless card in promiscuous mode, which was also known as monitor mode, right? Which is then ready to intercept data not destined to the NIC. A port has also been made to macOS called KissMac. It also incorporates automated passive web cracking and WPA dictionary attacks along with it as well. Pretty sweet deal. But the sweetest deal comes along with the aircrack-ng suite. And what's nice about the aircrack-ng suite is that it has a lot of different tools in it that we would use. And generally here we would use a couple of different tools in the real world, like your airmon-ng, which basically puts your network card into monitor mode, and as we mentioned, the promiscuous mode. And then we use aerodump-ng, which basically allows us to start packet capturing and saving it to a capture file. We then would use something like your airreplay-ng, for instance, to then replay those packets, disassociate and disauthenticate users off the network. And then we use aircrack-ng once the WPA2 handshake, for instance, has been captured, that we can then use aircrack-ng to actually then crack it and so forth. Now there are other tools out here too that can be used under different circumstances and such, but in general those four tools should be really the only ones you should be using when you're out there doing a real-world test. Depending on the situation, there are other tools like your PacketForge-ng, your East Side, West Side-ng, and so forth that can be used as well to actually create packets and so forth. So it's a matter of just checking each of these out individually and then trying it out in your environment to see which one will be the best fit.